All right, welcome everyone. Good morning, good afternoon, good evening. Welcome to the third day of the workshop. And today we'll start with Bowen Xiao, who will tell us about the Electron Ion Collider in China. So please go ahead.
Thank you. To save some bandwidth, I will just turn off my camera now. And let me go to the full screen mode. Okay. All right. First of all, good morning, good afternoon, and good evening. And I wish to thank the organizer for giving me the opportunity to present to you the updates on the scientific opportunities with Electron Ion Collider in China. And this talk is actually a summary of a collective work to promote EIC in China. Now the next page. Okay, so first, this slide is to preach to the believers of QCD and the EIC. Since the beginning of modern science, we have always been curious about the fundamental composition of dynamics of the physical world. And we wanted to achieve this goal, we have to understand QCD. And in particular, we want to understand the following big questions in the subatomic regime. For example, these questions are this first question is related to the spin of the proton, and then we also wanted to understand the dense gluon system. Also, we wanted to understand the proton mass. Actually, this is the hardest question because mathematically speaking, the mass gap in Yang-Mills theory is one of the 7 Meninian questions, Meninian problems in mathematics. We also wanted to understand how gluon bind quarks and gluons, and we wanted to map them inside the proton in a 3D fashion. We also recently wanted to understand the proton radius puzzle. In my opinion, the EICs will be the keys to unlocking all these mysteries. Next page. So now let me give you an overview of the proposed electron ion colliders across the globe. First, in the US, the REIC facility at Brookhaven National Lab will be turned into ERIC. For the US EIC, the critical decision 0, which is the mission lead, has been approved with the cost range around $2 billion, and it is expected that CD1 will be approved soon. This is about the selection cost and the schedule and the CDR approval. In Europe, there have been a lot of discussion about upgrading the LGC to EicC and also the FAIR system, FAIR to ENC. In China, we are now trying to promote EICC here, and based on the facility called the HEF. I will let you talk a little bit more about HEF here. Now HEF is the acronym for High Intensity Heavy Ion Accelerator Facility. It is currently under construction since 2018. It is located in a city called Huizhou, here. It is about 100 kilometers away from Hong Kong. Hong Kong is somewhere here, if you can see my cursor. The HEF has a total budget or a total investment of 2.5 billion RMB, which is more or less 0.4 billion US dollars. This is the timeline, the preliminary timeline of EICC. In China, now we are in 2021. HEF is halfway because since 2018, HEF is halfway in its construction. This preliminary timeline is more like a wish list to be blessed by the funding agency. It is technology driven. This is a technology driven schedule. And in 2021, between 2021 and 25, what we are trying to do is mostly simulations and detector R&D. And because in China, almost all the big projects are approved every 5 years. So this is called the 5-year plan. Our hope is that EICC can get funded in 2026, and then the construction will start immediately after the approval, and hopefully in 2032, we can have a EICC in operation if everything goes through. Okay, this is the conceptual design for accelerator and detector. In one of the interaction, as you can see, the EICC accelerator includes all these components. First of all, it's based on HF on the right, and then we have the P-ring to accelerate the proton and heavy ion to a higher energy. We also have energy recovery NENAC, and we also for the electron we have the source, polarized source, and injector. We also have the racetrack type electron ring. We also reserve 2 interaction points here, IP1 and IP2 here. In one of the interaction points, what we wanted to do is to put a general purpose detector with the following 4 components, as you can see on the right. On the left, the bottom left, you can see the conceptual design of the detector. This is the kinematics map of the EICC comparing with other facilities. On the left, I'm showing you the luminosity versus center mass energy for all the deep inelastic scattering facilities. And as you can see, the EICC covers the kinematic region between JLab experiment and the US EIC. And it has similar luminosity as compared to the US EIC. The energy is slightly lower. What we are trying to do is to focus on moderate X and the C-quark region for the spin and the exotic hadrons and the nuclear physics. And we also wanted to do some vector meson production to probe the mass of the proton. Recently, we have already finished the EICC white paper. It has been accepted, peer-reviewed, and accepted for publication in Frontier Physics. And if you click my PDF file, you can actually download the white paper. And this is the archive link. So the white paper effort is actually led by a team of 20 conveners, and it contains contribution from more than 100 authors from 46 institutions across the globe. Mainly, it has 4 parts. The first part is the summary, and we have the highlights. In the third part, we have the accelerator conceptual design and also the detector conceptual design. In the following of my talk, I will only talk about the physics highlights. Okay. So let me begin with the 3-dimensional tomography of proton. First, let me begin with the Wigner distribution. Wigner distribution is usually called the mother distribution of all distributions, because it ingeniously encodes all the quantum information of how partons are distributed inside the hadron. If you have the Wigner distribution, then you can actually obtain the TMD. You can also obtain the impact parameters by integrating either over the impact parameter or over the transverse momentum. If you integrate both, then you will actually get the so-called Feynman parton densities. The impact parameter distribution is actually related to the GPD, which is very important for us to understand the mass distribution. as I will talk about in a moment. Let me begin with spin. If according to Jeffrey Manocha decomposition, you have 4 components. You can break the proton spin into 4 components. You have the quark part, you have the gluon part, and the quark part can be further decomposed into the quark's helicity part and the angular momentum part. In terms of G1 structure function, actually we can access this delta sigma. The delta sigma is the quark spin contribution. Now we understand is much better, and it is roughly 30% of the proton spin. And at EICC, we are going to measure it much better with more precision. And the goal is to understand further the angular momentum part and also the orbital angular momentum part. I want to also mention that the lattice QCD can also help us to understand this further. And for the spin flavor structure, what we can do is to focus on the C-quark distribution, C-quark helicity distribution, and we are going to have more precise data for C-quark helicity and significantly reduce the spin contribution from the C. And we also have the polarized, because we have polarized the electron and the proton, as well as helium-3 here, as mentioned here. Let me also mention a little bit about the gluon helicity. At EICC, what we can do also, of course, at EIC as well, what we can do is to tag a D meson. Because the D meson has to come from the gluon. So EICC can help us access the gluon helicity in moderate and high X region. If you compare the EIC energy shown here in green, you see all these above 3 are for the EIC energy, US EIC energy. As you compare all of them, you can see that EICC can do a little bit better in the large X region, but just 1 point, but it's slightly better. And the uncertainties are shown here on the right side of the plot, on the right side of this plot, delta G over G absolute uncertainty here. And we also can access quark-Sieverts function, especially the strange quark-Sieverts function via semi-inclusive DIS. So in a leading order analysis of the EICC projection, what we can see here is we can measure the up quark Sieverts function and down quark Sieverts function in very precisely. And because the S quark Sieverts function has never been measured before, so we don't have any data at the moment, but what we can show is that we can reduce the statistical uncertainty, and we can have very small statistical uncertainty, and as well as the systematic uncertainty for the C-quark Sieverts function. And let me go through a little bit the GPD from DVCS and DVMP. DVMP is the deep virtual meson production. So in these two kinds of process, what we can do is to understand the GPD H and GPD E, because they are related to the total spin of quark and total spin of the gluon. By measuring those constant form factors, CFF, we can measure the GPDs. It allows us to understand the spatial distribution the quarks inside the nucleon. And we also can indirectly get the information about the quark orbital angular motion. And let me, because this workshop is about the proton mass, we're more interested in the mass. So I have the following 2 slides about the proton mass measurement. So in a 95 paper by Xiao, he managed to decompose the mass of the proton into 4 pieces as well. So you have the quark energy piece, you have the quark mass piece coming from the quark condensate, and you also have the gluon energy piece, and the last one is the trace anomaly. So in principle, you can measure the MQ and MG from the PDFs, and you can also measure the mass of the quark contribution via the pion nucleon low energy scattering. This is laid out, I believe, in the yellow report of EIC. And the last piece, unknown piece, is the trace anomaly energy, or sometimes we call the quantum anomalous energy, MA. One proposed that starting from more than 20 years ago, DIMA proposed that you can measure this quantity, or you can access, or at least constrain this quantity via the threshold production of GIPSI, or upsilon. You need to have the heavy quarkonium to access those gluon anomalous gluon contribution. This is shown here. To 8.2 is the energy, the threshold for GIPSI, and also the upsilon has the threshold of 12 GeV. So this means that it's EICC actually has the low energy, low enough to probe the upsilon threshold. For EIC, in terms of upsilon threshold, I believe the upsilon threshold is located in the low Y region at US EIC. So in principle, essentially, there is a complementarity between the EIC and the EICC, as well as the lattice QCD. Lattice QCD can also measure or compute all these contributions from various parts of the energy. And I wanted to also mention this gravitational form factors, because this is very hot recently, especially after the recent GlueX data at JLab. So intuitively, you wanted to measure the gravitational form factor or the mass distribution of the proton by exchanging a graviton. Exchanging a graviton between your probe and the proton. This is kind of similar to charge form factor, because if you wanted to study the charge distribution of the proton, you exchange a virtual photon with the proton target. What you want to do is to have a colorless exchange, because if you exchange a gluon with the target, then you're going to break it. So you are going to break the proton. So that's something that we don't want to do. So on the other hand, if you exchange a graviton with the proton, then it's very hard to measure, because gravity is, we all know that gravity is too weak. In 1997, actually, Xiao proposed to use 2 photons, which they have spin 1. Each photon has a spin 1. They in deeply virtual complex scattering to study those GPDs. These GPDs are related to the gravitational form factor. This allows us to indirectly study the mass distribution. In addition, as I showed here in the middle and on the right, you can see that there are actually 2 channels to study the energy momentum tensor, T mu nu, of the proton. One is through the quark channel you have as shown here. The other one is that you first allow the virtual photon to fluctuate into a QQ-bar pair, and then the QQ-bar pair exchange a pair of colorless gluons with the proton target to allow the target proton to be intact in the final state. In the final state of the on this side, we can either have a photon back, or you can measure, or you can produce a J psi or upsilon. Ideally, this will allow us to probe the electromagnetic component of color electromagnetic component of the proton target. I also mentioned a little bit earlier that there has been a strong impact of the recent GLUX data on the extraction of the mass information. There have been a lot of papers since then, and about the mass radius, and I believe there's if we have the synergy between the EICs and the theory, including lattice, we are going to understand the mass distribution and the mass property of the proton and other nucleon, and also other nuclei very much better. And
excuse me, you have 5 minutes.
Okay, I'm almost done. Thanks. So on the right, bottom right here, the highlighted yellow region are shown here. These are the EICC kinematic region, which allow us to really sitting in the sweet spot to measure the threshold of BB bar and the upsilon vector measure. So I want to go through a little quickly about the quark gluons in cold nuclear medium. So in EICC, first we can actually measure the nuclear PDF, and we also can use the heavy nuclei to study parton energy loss in cold nuclear medium. We can also, because if you scatter a virtual photon in on one of the nucleons inside a heavy nuclei, you can see that you can strike out a parton, and this parton can lose energy inside the cold nuclear medium, and it either can hadronize inside the nuclear medium or outside the medium. But this is something we want to study. So we want to use nucleus as a lab at the Fermi scale. And we can also study the exotic states at last. So it is complementary to the E plus E minus scattering and the PP collisions. So there have been a lot of exotic hadrons and tandem quark hybrid state and global. What we wanted to do is to build a detector with large enough acceptance to measure those exotic hadrons and make sure they produce at the mid rapidity. And if we're specifically interested in the heavy flavor exotic hadron, in particular Charmonian-like states and the hidden Charmonian pentaquarks. And the polarizations of electrons and the protons actually allow us to determine those quantum numbers according to our R&D study. So let me come to the summary. I would say that QCD is discovered 50 years ago, and on the other hand, there are still more questions than answers in QCD. We have a lot of work to do, and the cutting edge electron ion collider will complete our 21st century view of the proton and render us this 3D imaging of hadrons. And EICC actually is focusing on the C quark and at moderate and large X region. And we also wanted to understand the mass through the upsilon production. EIC and EICC actually, they are complementary to each other in the physics code. Thank you very much for your attention.
Thank you very much for this very nice overview. So we have time for questions. I see Victor has raised his hand. Please go ahead.
Thank you very much for very interesting and encouraging talk on new era of QCD in China. I have one comment and one question.
Mm-hmm.
My comment is, you mentioned Hall-D result and impact of this result into the emergence of hadron mass understanding. I want to pay your attention, however, also to Hall-B DVCS result, which offer insight into the pressure distribution inside nucleons. These results are published in the Nature paper. And recently, we have another result which provide insight into the shear forces inside nucleon. Certainly, constraining this ingredient offer valuable constraint on the generation and distribution of the nucleon mass inside the nucleon. And my question is, you advertise vector meson production, I believe high mass vector meson, J-psi and epsilon, as a tool to see how mass emerges, how mass of nucleon emerges. My question is, do you have any relation between vector meson production observable and mass distribution or mechanism underlying mass distribution in order to see sensitivity of the experimental data to mechanism or interpretable in QCD observables on nucleon structure you want to extract from the data?
Thank you first of all for your comment. Actually, I was actually reading about the pressure and the pressure, and also the shear pressure, the data actually, and the paper last night. I didn't have. I will certainly put those into my future slides. And as to your question, thanks for that. As to your question, I believe the connection between the mass and a very rigorous connection between the mass and the measurements, especially the upsilon measure, is not yet very cautious, in my opinion. We still have a lot of work to do because this is a very complicated region, because in the near the threshold, many other twist contributions become important, and there are higher twist contributions, that there are other stuff, and also we are seeing, in order to produce this J-psi and epsilon, we have to have very large momentum transfer instead of a small momentum transfer. The T here, T actually has to be large, not instead of small. So I think there are still a lot of things for us to understand, and I believe we still have years to come to work this out. Thank you.
Thank you. Are there further questions?
Can I ask?
Yeah, please go ahead.
Yeah. Have you any observation the decrease of the neutron mass in medium compared to the free state of the neutron? Do you understand my question?
Sorry, can you repeat it again?
Yeah. Have you any observation the decrease of the neutron mass in the medium compared to the free state of the neutron?
Yeah. Actually, so you're asking me about the free neutron mass, the difference between the free neutron and the neutron in a nuclear medium. Is that right?
Mm-hmm. Yeah, yeah.
I'm sorry, actually, I don't know this, but actually it could be a good problem to. It could be a project for us to study in the EicC, because we actually can measure. But I don't know how. But it could be a project to work on at EicC, because we do have cold nuclear medium, and we just need to figure out how to study those the mass of neutron inside a cold nuclear medium.
Yeah. Thank you.
Thank you.
All right, thank you. So I don't see any further hands raised, so I suggest let's move on. So thank you again for this nice talk.
Thank you.
and then